Okay, thank you for the introduction, and especially thank you for everyone who is brave enough to stay here for the last talk. I'm going to talk, well, again, about photoacoustic tomography, and we were mostly interested in this project in getting the deep learning iterative framework working for our experimental data. So that means we're working now with subsampled, limited view 3D data, and that comes with some problems. And also to tackle this, we need a rather large team. So that's where I belong, to the Center for Medical Image Computing at UCL. We did pretty much all the computations. Then we had backup from our medical physics guys who built the experimental device to take the measurements, and also to develop the simulation code. And then we had some backup on deep learning by Jonas Adler from KTH, who gave a talk earlier today. Good, so I'll give another introduction to photoacoustics so that you have now an idea of what we're dealing with. Then we have our special sensor that is a limited view, so we only detect from a plane. And to solve such problems, as we know, we use iterative reconstruction schemes to get nice reconstructions. Then we combine this with deep learning, and since we're from the Center for Medical Image Computing, we're very much interested in the computational results. Good, so let's go to photoacoustics again. So as we heard, it's a method from coupled physics, or also known as a hybrid inverse problem, and we start with the optical part. So here we have a chromophore concentration that defines our optical absorption coefficient. So here, a randomly chosen coefficient to illustrate our problem, and so now we illuminate this target with a laser pulse, so like this. So we illuminate this, and then the tissue will absorb the light, and that leads to a thermalization. So the light will be absorbed. That leads to heat up, and with this heat up, we have a local pressure increase, and that's the acoustic part. We concentrate now only on the acoustic part, so that's the linear part of this problem. So we take this as a starting point. We have here our local pressure, P0, and then this propagates as a wave throughout the tissue. And we can then detect this here at the boundary. So here you see that at T equals 0, we have our initial pressure. That's our initial condition. So let's have a look. So here's our initial pressure, and then, we simulate the PDE, and we have a nice propagation of the wave. And ideally, we want to measure now for all times where this wave is non-zero on this full surface. And that defines our measurement. So here, for 2 dimensions, we have a circle. For 3 dimensions, this would be a sphere. For instance, could be also other geometries. And then we take our measurements for all times where this wave is non-zero, and that is our measurement. So here for all r on this surface. And then the mapping from the initial pressure at T equals 0 to this time series on our surface, that is a linear problem, and we will write it later simplified here with this operator A. X will represent our initial pressure, and Y is our time series. So that's the classical inverse problem framework. Good, so now we have our measurement. What we can do, if we have a complete information of the measurement, we can just backpropagate it back into the system. So with here now a Dirichlet boundary condition in time, and that is our measurement, and we just backpropagate it into the tissue or the target, and we get, actually, if we have full measurements, we get a really nice reconstructions. So here in the beginning we just see small variations, and then the wave will backpropagate inside, and we get pretty good reconstruction. So disregard those parts, those are not really in the tissue, so those are just computational artifacts. Good, but as we know, for an iterative process, we actually don't need some inversion algorithm, we rather need the adjoint. And adjoint here is defined in the L2 sense, so here we have our forward operator acting on the initial pressure, and the adjoint acting on our measurement. I'm not going into the derivations here. If you're interested, I recommend this paper in Inverse Problems, where this is better described. But actually, if we have full measurements, this adjoint acts very similar to time reversal. So here we see again, it back propagates, and we get soon a pretty good reconstruction, actually just by back projection with the adjoint. So also we need to solve a PDE, and we get here pretty good reconstruction just by back projection with the adjoint. So let's compare. We have here a bit of a different scale, so there's a contrast difference, and there are some minor artifacts here. So that's not really major, but since it's just the adjoint, for that it's pretty good. Good. So that was the photoacoustic problem. Let's now go to our limited view problem due to the scanner we're using. And that is a so-called Fabry-Perot ultrasound scanner. So we actually detect the pressure wave with an ultrasound scanner. So we illuminate here our target with our laser, and then, well, the pressure wave again distributes towards our sensor, and the sensor here consists of a small polymer film, and that will change in distance when the pressure wave hits. And we can read that distance out with an interrogation laser, but that is pointwise. So if we do this for each point, we have quite nice measurements, but our limited view geometry will lead to severe deterioration in the reconstruction. So here again we see time reversal, so that's the back propagation of our measurement inside the domain. And we see, well, we get on the top reasonably okay reconstructions, but especially here the letters are completely masked, and we need to do more to get there actually a nice reconstruction. But also we need to scan in each point of this scanner, and that's how the scanner is built. So we have to illuminate once, we can only interrogate one point, and we need to do this for each point. If we do that, well, we do get very nice reconstructions. So here that is an actual mouse liver from this target. So, but we see here, at least especially in the lower layers, we don't get so nice reconstructions. And also you might imagine this takes quite some time to get a full measurement, so we want to speed that up, and for that we only required by compressed sensing, we use subsample patterns, and that interrogate only a part of the sensor. And then we know subsample data, limited view, we need to do something more for our reconstructions. And a classical approach here is the variational reconstructions, where we have now X as our photoacoustic image, so that's the initial pressure, Y denotes our time series, and we want to reconstruct our image as a minimizer of such a penalty function, where D has a data fidelity term and R enforces some kind of regularity to our reconstruction. And a very simple approach to do that is given by proximal gradient descent, where we take a gradient step with respect to the data fidelity term, and then we solve this, we apply this proximal operator that solves an image denoising problem that incorporates then our regularizer to the problem. So, and we will then later, motivated by this, also formulate our deep learning iterative scheme. And well, let's have an example. One, probably the easiest choice here, is the non-negative least squares. We choose now the data fidelity as the L2 distance, and take here the proximal operator to just enforce non-negativity. So because we know our initial pressure will be positive, so we use a non-negativity constraint, and Rx is then just 0 if x is positive, otherwise infinity. So the proximal operator reduces to just the maximum or the projection to the positive numbers. And then very popular choice is, as we all know, TV regularization that enforces sparsity in the gradient. Good. Let's see how that actually works. So now we have here a toy example to illustrate this. Here we have some tubes that go through the domain. In red we have the sensor, the position of the sensor, and this is our subsampling pattern. I think it was 16 times. And that's a slice through the target. If we backpropagate fully sampled data, but limited view, fully sampled, use the adjoint, then we get, well, a reasonable good reconstruction. But we see clearly limited view artifacts here in the lower layers, and there's those artifacts that go from the tubes. If you have subsampled data, that deteriorates quite a bit, so we get also a lot of noise in the background and not really sharp reconstruction. Then if we just use non-negativity for the fully sampled, and then iteratively solve this, we get pretty good reconstructions. So that's actually really nice, just by non-negativity. But for the subsampled, we do have here, that's a bit unsharp, and we have some noise in there. And using TV further improves this, and we get nicely cleaned reconstructions and rather sharp edges even in the lower layers. But we need to do that iteratively. And since we're now in 3D and we're solving actually, in each of these iterations we solve a wave equation and a adjoint, which also solves the wave equation. So that takes quite some time to take this 20 iterations. So we want to speed that up by techniques from deep learning. We've seen that all, so short reminder, I can do that rather fast. We have a small convolutional network with 2 layers, and we call those now channels. And those channels are produced by several filter matrices, so that's just a convolution matrix and a bias for each of those channels. And then we separate this to 3 channels, we combine this to 2, and then we get our output f. And we apply here also our nonlinear activation function is chosen as rectified linear unit, or the projection to the positive numbers. Good. So, and then we denote now our network with G and the parameters theta, which are those matrices and scalars. And then we want to minimize the loss functional to obtain our optimal parameters that minimize this penalty term with respect to some training data. So we've seen that today already quite often, so let's go further. So as we've maybe some heard today also, there are 2 different fundamentally different approaches for image reconstruction with deep learning. The first one is we take a simple reconstruction, like applying the adjoint, or in CT use filtered back projection, and then train a network to remove artifacts. And that in many applications actually is rather powerful and especially fast. But for our limited view problem, we motivated that it would be better to take an iterative scheme. So to update with the gradient information in each iteration. And those are the so-called model-based learning approaches, where we heard today from Jonas and Ozan, nice talks about that. So, and we go now through both of those. So this is definitely not an extensive list because there's so much happening. On the direct post-processing with convolutional networks being applied to sparse angle CT, low dose and limited angle CT, 2D photoacoustic tomography, MRI, dynamic and undersampled. And they perform pretty well. And they're all based on the same structure, we heard that today, the UNet. This UNet is very popular, especially it won those 2 very prestigious challenges at the International Symposium for Biomedical Imaging, I guess. And it's based on this multi-level decomposition, you could say. So here there's the input, it goes to the small numbers depict the channels of our convolutional filters, and then they're downsampled to lower resolution and to here to the lowest level, and then built up again and combined with those skip connections, which is a concatenation, so that also the higher levels propagate. It also stabilizes the training procedure. And the output in this original unit is a segmentation mask. And what all those studies I showed before did, they used a residual unit. So first, you need to make sure that you have spatial consistency, because you want to have the same resolution in your input as in your output. And they reformulated this to a residual network. So they have another connection here from the input, and there's an addition to the output. So now the network learns how to remove artifacts from an undersampled image. And that we will see later also, we implemented that also for our problem, actually works reasonably well. And then are the model-based approaches, where we want to learn an iterative scheme that incorporates our physical knowledge of the problem. And, well, by Jonas and Ozan, we heard today, oh, nice typo, and, well, there are the applications to CT and MRI. This group actually even learned the filter functions, so the nonlinear activation functions. That's actually pretty nice. And, well, and those did it for image super resolution and denoising, where they basically learned the whole procedure as a CNN. Yeah, but what those all have in common, they predefine an amount of iterations, and then they learn the whole iterations, and well, they also interpret each iteration as an own layer and learn it all together. That is for us not possible, because the computational bottleneck in our 3D photoacoustics is the simulation of our forward and the adjoint. Compared to CT and MRI, they have complexity, the forward operator, n cubed, and we have one more due to our time component. So, and for me, simulating for our 3D volumes, my forward operator on my GPU takes about 12 seconds. So that is quite long. And if we would do that in the training, that would be, well, extensively long. So what we need to do is we have to train each iterate separately. We can't train the whole network together. We need to train each iterate gets an own network that we train separately. So let's go back to our motivation. We have the proximal gradient descent scheme. We have here the gradient of our data fit, the current iterate, and motivated by this, we put those two components into our convolutional neural network, and now denote each network here the parameters theta k for each iterate. And then we want to learn how to combine those two components to get the next iterate. And we chose here now also the L2 distance for the data fidelity. So here we have the joint and the forward. Good. And we call this the deep gradient descent. So we input here our iterate, our gradient. Those are the channels of our convolutional layers. So we put this to 1632. Then we add those together and then reduce again to 16 and 1. And also we learn a residual here. So we learn the update for each iterate with our network. And at the end we project that to the positive numbers because we want to have our reconstruction each iteration to be non-negative. Good. So then a short note on the difference between the full iteration and the separate iterative networks. So if we have a network where we have a predefined number of iterations and learn that together, what we're essentially minimizing is the output of the last layer to our desired image. And that is the error that we minimize. In our case, we can only minimize with respect, so we can only minimize the current iterate and take the difference to our desired output with respect to the output of the last network that is already trained. And clearly this is an upper bound to this. We can, if we have a predefined amount of iterations, we will definitely get a better result here, or at least as equal as good. But here we are sure that we actually improve in each step. So we are not really constrained at the end to take all of our iterates that we trained. We can also take a subset if we may be short on time, which is also nice. Good. So let's see how that works in practice. And the first problem we came across is what we want to measure are vessels. So mostly in photoacoustics you're interested in vessels. But how do you get a large data set for training of three-dimensional vessels? So what we did is we went to a publicly available data set of whole lung CT scans. So we took 50 CT scans. Might sound weird, why did we do that? But then we segmented the vessels out here. So here you see vessels, there you see vessels, and we took that as our ground truth as vessel data. So here you see very crude segmentation of the vessel structures. There might be some artifacts from the segmentation, but those are data. So that is just smaller structures in your target, so that's fine as well. So we learn here how to reconstruct those vessel structures. And then we got 1,200 volumes of 80, so that's the depth, and 240 times 240, that's basically the resolution of our scanner. And then the training, we minimized the L2 distance and trained each network for 50 epochs. An epoch is a full cycle through the training set. And well, the training of each network already took in 3D 1 day. So we had, and at the end we trained 5 iterates. So only the networks, that is 5 days of training, plus pre-processing. So first we need to train the network, then we need to pre-process, compute the gradient, so forward and adjoint, to train the next network. That took another 12 hours. So in total we ended up with 7 days of training for one iterative deep gradient descent with 5 iterations. And now, if we would have done the full training approach with 50 epochs and 5 iterations, my rough calculations where we end up with about 70 days. Maybe that's possible when the hardware improves, but at the moment, no one wants to wait that long. 7 days is already pretty tough.
Which hardware did you take? Which hardware did you take?
That was on Titan XP.
1.
Yes. Yeah. Of course, if you parallelize that with multiple ones, go on a... Okay, I had only a workstation. On a workstation, this is not feasible. Good. So, let's go then to the results. Here we have our phantom, so that's a maximum intensity projection from the top. So just imagine you look from the sensor inside the target. And then we see here, that's the initialization, that's the back projection just by the joint, and it is actually pretty good. So it's quite nice, but also, well, the noise level was chosen to be about that we had in our measurements in SNR of 10 to 15. So that's about the noise level of our sensor. And well, if we take 5 iterations of our deep gradient descent, visually that's pretty good. So we get even here the small details recovered. And well, there are some differences, very fine differences here on the outer parts. And that's very typical with the limited view geometry. And now we want to compare this to the post-processing with UNet. If we have the maximum intensity projection, well, they both look pretty good, to be honest. So there is definitely value in the post-processing. But if you look at the difference here, so blue is a negative difference and red is a positive difference to our desired phantom, and they're both on the same scale. So here for UNet we see that there's actually quite a substantial difference in the error. And especially here, while we see on the boundary, and while this is a side view, we see that they are still connected to the limited view artifacts. There's a bit still present. Well, this is quite strong here for the UNet. And of course, post-processing can only reproduce what has been present in the first initial reconstruction. So, and quantitatively, we were quite interested how we perform. We took a bit unusual error here, mostly because our network knows that our intensity is always between 0 and 1. TV doesn't know that. So we didn't want to penalize TV just by having a difference in the contrast. So we scaled this. And in photoacoustics, actually just the relative contrast is of importance here. So we want to have a nice image that we look at. And the errors, well, UNet actually does pretty well. It's a huge network. So not surprisingly, it actually does better in the first application than our iterative algorithm, because our network is rather small. But then already after 2 applications of our deep gradient descent, we have a better reconstruction. And we go down here to down to 15. So one thing important to mention is all done for test data. So that's what not included in the training. And compared to TV, you see this actually converges very slow. And that's mostly, I think, because the network can figure out in the first iterate already the contrast really nicely. So that has a huge effect on the error. And here we take note, this is nonlinear. We have 50 iterations of TV are about as good as 2 iterations of our deep gradient descent. So it's a speed up with the first application of the adjoint for the back projection of times 20. That's quite considerable. But then, yes, everyone who worked with real data knows this problem. You have a really nice working algorithm. You go to real data, experimental data, and, well, it doesn't work so well. Here we see TV reconstruction from fully sampled limited view data. It works, but our pre-trained network doesn't perform so well. So we need to do a bit more. And what we did, we identified that the main problem is that our network takes everything as feature, which you have in biological tissue. You have a lot of low absorbing regions that contribute to our signal, and that will be reconstructed. So we somehow need to teach our algorithm to threshold low absorbing regions. And we did that by adding a Gaussian random field to our phantoms, then simulated the data and back projected that with additional noise and took that as our initialization. So here we have an added Gaussian random field in the background to simulate low absorbing regions in biological tissue. And we trained the network to reconstruct the clean phantoms. So of course, the reconstructions will be as good as before, but we teach basically to threshold low absorbing regions. And that worked already quite well, but we still can further improve this if we have some reference data sets. So here we see a small set of measurements from human targets, and we took about 20 to then do an update training of our network with a small amount of epochs and a small learning rate. And those are now fully sampled reconstructions from finger, wrist, and palm. Those are actually 2 fingers side by side. So, yeah, and doing all that, we got quite nice results. Here we say again the back projection. Here, that's our deep gradient descent trained on the background added data, so without update training. And here we see the network with the update training. So to also include some information of our measurement device. And on the bottom, we have 2 TV reconstruction of the same subsampled data with an emphasis on the data term and an emphasis on the regularization term, because we couldn't decide which one is better, so we took both. And here, that's our reference, a fully sampled TV reconstruction. Okay, let's put them side by side. So here we have the updated one, and actually it has quite a few nice smaller details here that are gone in the TV reconstruction. So this is the one emphasis on, yes, the data. So here they are, especially in this region, a lot more smaller structures. So you can ask yourself, how do we know that those are actual structures? And our clue is, well, we look at our fully sampled reconstruction, and they are also present there. So at least from the point of view of a photoacoustic image, this is pretty good. And we took only 5 iterations compared to TV with 20 iterations. So that's also a speed up just by 4 times here, but that is considerable taking into account the computation times. But then, yes, the big question that we all struggle with is the generalization. what if our geometry changes or even our targets slightly change? What happens? Do we have to retrain the network to adapt to every possible setting? If we want to achieve the best results, I would say yes, we have to. But at least empirically, we can say also, we saw today with ozone, that iterative networks are a bit more robust to changes. And we tried that. What happens? So we first perturbed our forward operator. We used a different sampling pattern as in our training. And at least qualitatively from the images, there's not really a big difference. Still, we have the nice small structures reconstructed here, but actually quantitatively there is a difference.
What is the perturbation?
So here we used the same subsampling pattern uniformly sampled in the training, and here we just used a different one, a different subsampling pattern. And it actually had already quite an effect. So the first iterate maybe not that much, but in the later ones there's a difference about 5% in the relative error zone. That is just by changing the subsampling pattern, which might be a bit worrying. But also then if we change the phantom. So now we applied our deep gradient descent to a phantom that includes a tumor. You might be interested in measuring that in a human target. You see that actually the vessels, they look very much like our training data. So our algorithm really learned how to reconstruct those specific vessels. And I would actually rather say this is rather well reconstructed. And from error-wise, I didn't plot it here, but it achieves the same error as 25 iterations of TV. So it actually is still can be considered as rather robust here. But UNet, comparably, so if you do the post-processing, you see that there are introduced a lot of structures in the background. So I don't know where they come from, but UNet introduced a lot of noise there in the background. And if you have a look close up, maybe you see it. Those are quite, the background is nicely uniform. Here you see some noise, and there are some funny halo artifacts around the vessels. So that actually gives us some backup that actually the iterative approach might be a good idea in those tomographic methods to actually have some robustness and consistency in reconstructions. Good, okay, then let's wrap up. What we've done is our goal was to actually work with real experimental data, so subsampled 3D limited view, because our sensor is limited view, and we had to separate the training to learn each iterate separately because of the high complexity of our forward and the joint. We trained on segmented lung vessels, and with some modifications like adding this background, we were able to even apply it to our measured human data. So that's quite nice. What's to do? Well, a lot. What's ongoing, what we can consider next is, you might have noticed, that's a bit worrying. We only optimized on image error. We didn't actually enforce any data consistency here, so that's something we have to do. To also enforce data consistency, that actually our new reconstruction fits also our data, as we always want in inverse problems. Also, while the network was rather small and more empirically chosen, we could definitely use some more sophisticated network structures, but then we run also, at least I run on that in my workstation, on problems, memory limitations. So my GPU was already maxed out of that. And then the biggest question, what does our convolutional neural network actually learn? We like to think that actually it learns a prior for our vessels, and we saw at least the reconstruction on the simulated tumor phantom learned the same structures to reconstruct the vessels. So, but how to get those priors out of the CNN? That's the big question. Thank you.
we have time for questions. Actually, plenty of time. So I have a question. So I don't know a lot about the use of CNNs for inverse problems, but the fact that you use a convolutional network sort of encodes the fact that you expect some shifting variances at the first layer.
Yeah, that's
angle tomography that probably doesn't.
That is a very good question. There's a bit of a problem because the artifacts, the limited view artifacts in the lower levels are definitely not translation invariant. So it would be probably better to use some network structures or elements that do take spatial information into account. Yeah, that is definitely something we were thinking of, about, but so far we didn't incorporate.
And in the first convolutional layers, how do you do the boundaries? What do you do?
That's just, so we just pad to the same region. So, yeah.
We used some UNet segmentation for vessel segmentation in retina images and recognized that when you train it with the wrong scale or with the wrong diameter, that the reconstructions show a halo type artifact.
Okay.
In the wrong segmentation, or at least they show artifacts that you would not expect, and they look like also
Okay.
so that might be one reason. My question is, do you have you observed something with respect to scale? Because you have a lot of different vessel diameters in your reconstruction.
That is a very good point, because I think our segmented vessels were all very much the same, about the same thickness. I had just computed the two more last week, so I didn't have much time to look into, but that's a very good point. I can't comment on it, but I will definitely look into that. Yeah, it's interesting.
So in the TV reconstructions, are you enforcing simultaneously TV and non-negativity?
Yes, of course. That also has non-negativity in there. Yeah.
Any other questions?
Well, I think we're all tired.
That's it for today. We're all done.